So now it's recording. So yeah, we are talking about deep learning and neural network. In the first session, I gave you a brief summary of the neural network. That was a brief introduction to neural network structures, and then I talked about the activation functions, which are done on each nodes of the layers in neural network. And then this session is allocated to just the activation functions because they're very important. And without activation function, the neural network doesn't work. So on each node or on each core of neural network, these units, this is the activation function that run the neural network, that do the calculations and generate the outputs, right? And then I said that for deep learning section of this course, we're going to use Tensorflow package to call the neural network functions. And then this was a small code in Python using Tensorflow that we can create, for example, this neural network structure. So first we import TensorFlow as TF, and then from TensorFlow cross. As I mentioned, cross these days is part of the TensorFlow. So from TensorFlow, we can use cross and then import the sequential. Sequential is used to string together these layers, right? For example, our model would be the sequential of 3 layers, right? Because we have 1, 2, 3. We usually don't take or consider the first layer or the input layer, and then we start from the hidden layers and the output layer up to output layer, right? So sequential means a string 3 layers together. The first one, this layer, we use dense function. Dense is a type of a layer. This is the type of this layer is dense. So dense, how many units we have on this layer, on this dense layer? 25 units. So units equal to 25. And then the activation is equal to, let's say, sigmoid. Because in the previous session, we just used sigmoid function as an activation function on each node. Let's continue with the sigmoid function. And in the following slides, I'm going to introduce new activation functions, and then you can use them for your different layers in neural network. But for the sake of simplicity, let's stay with sigmoid function. So the activation is sigmoid function. And then for the second layer, this one, using dense method, the unit in this layer is 15. And then the activation function is sigmoid. And then the last one, again, dense, and the unit is just 1. And then the activation function is sigmoid. So this is our model. And then this sequential string these 3 layers together, right? And then from TensorFlow cross losses, we import a loss function. You remember the loss function, right? From logistic regression. So in logistic regression, when we wanted to introduce the cost function, we introduced the loss function first. So the loss function for here, let's say it's a binary cross entropy. Let's say our application is a classification and it's a binary classification. It means our output has just 2 classes or 2 categories. So it's binary. Binary means 2 output. Binary cross entropy. I'm going to talk about the loss function in details in the following slides. Please turn off your mics. Heina Dong. And then here in this line, our model, which we created on the top here, we compile our model with a loss function. And our loss function, let's say, is binary cross entropy because we are working on binary classification application. And then we fit our model on the training data set, X and Y, with 100 iterations. Epochs means number of steps in gradient descent. Number of steps that we allocate to gradient descent to run again and again to optimize the model parameters, right? To minimize the cost function or loss function, and then give us the optimum model parameters. And then from those optimum parameters, we have a comprehensive model, and then we can make a new prediction. If you give a new data, new input to your model, then you can make a prediction in an accurate way. So what was the first step? The first step was specify how to compute output. Output, given input X and parameters W and B. You have to define your model. It's a regression, it's a linear regression model, it's a logistic regression model. It is, you're going to use the neural network, what your model is, right? F of X. Remember, F of X is our model, which gives the output or the target value, right? And you remember that for logistic regression, the Z was WX plus B, right? The dot product of W and B plus W and X plus B. And then the F of X here, the F of X, which was equal to G of Z, right? You remember, which gives us the output, the probability of being one. You remember that in logistic regression, the output F of X shows the probability of Y being one, right? For example, the probability of a tumor is cancerous. If F of X is 0.7, it means 70% chance that the tumor is cancerous or a t-shirt is a top seller. And then F of X in logistic regression was 1 over 1 plus exponential of minus C. And Z was WX plus B. And then in the logistic regression chapter, we introduced the logistic loss. You remember this log function for the loss, which was minus y times log of f minus 1 minus y times log of 1 minus f of x, right? And then in the last step, to minimize the loss function, because loss function shows the difference between your prediction and the actual and true value of your test data set. So when the loss function is huge, if it's a large number, it shows the difference. You couldn't fit your model very well on your data. That's why there's a huge difference between your model and the existing data set. So the purpose, the final goal is to reducing the loss function. Reducing the loss function means that your model is fitting the data better and better, more accurate. And for doing this, we use the gradient descent, you remember, to minimize the loss function. And these two lines shows the process of gradient descent to updating our model parameters W and B. Using the initial value of W and B, the learning rate alpha, and the first derivative of our cost function j with respect to w and b. We talked about all these steps in logistic regression chapter. And you remember that that was the loss function, right, in logistic regression chapter. Loss of f of x and y, our prediction and the true value y. And then j, the cost function, was the actually the mean value or the average of the loss function, because we have a summation all over the data set divided by the number of data set training examples. So this is the average loss function, average of loss function, which is called the cost function for the logistic regression. And then we train our model on the data to minimize the cost function j using gradient descent. But this column was related to logistic regression. Right now, let's do the same thing for neural network. So how we used to create our model in neural network using a sequential, right? We string together these three layers, like here on the top, right? We have, let's say, three layers, two hidden layer, one output layer. This is my neural network model, right? And then you remember, for example, for the binary classification, we use binary cross entropy as a loss function. So we compile our model, our neural network model, using a loss function, this loss function, equal to binary cross entropy. And then in the last step, we feed our model over the data set, X and Y, with 100 epochs or iteration. This epochs or iteration shows the time that takes for gradient descent to generate the optimum model parameters W and B for our model, right? Any questions so far?
No sé.
And here in this part, we're going to create our model. So again, uh, let's say that this is the structure of my neural network. So the first hidden layer with 25 units, the second one with 15 units, and the last one, the output layer with 1 unit. And you remember that on each layer, we have number of nodes or number of units, right? So for example, in the first unit, we have W and B, right? The second unit of the first layer, we have W and B. Or for example, for the 25th node or unit of the first layer, we have W25 and B25. And then the superscript shows the number of layer. It's a numbering for layer. It's an index for the layer. Because we are on the first layer, the superscript is 1, 1, 1, 1. For example, in the second layer, the superscript is 2, 2, 2, 2. And we have 15 units. So on each unit, we have W and B. For the first one, W1, B1. For the second one, W2, B2. For the last one, W15, B15. And then in the last layer or the output layer, we have another set of model parameter, W1 superscript 3, because we are on the third layer, and B1 superscript 3. And then the output of the whole neural network is A, this activation value from the last layer or from the output layer. So this was the code that we used in the previous slide, right? We imported the TensorFlow as TF. From TensorFlow cross, we imported sequential to string the layers together, right? And then from TensorFlow cross layers, we import dense. Dense is a type of this layer. So our model is a sequential of 3 dense layers. The first one with the 25 units and sigmoid activation function on these nodes, on these 25 units. Second layer with the 15 units and the sigmoid function on each 15 units as an activation function, and the last one with 1 unit and the activation function, the sigmoid activation function, right? And about the logistic regression, you remember this was the loss function for logistic regression. L of f of x and y was equal to minus y log of f minus 1 minus y log of 1 minus f of x. And then we use this loss function and this expression here and get the average of it. And this gives us the cost function j, which is function of w and b, the model parameters, right? So this cost function j is a function of all the w and b's, which are in our model. And gradient descent minimize the cost function j to give us the optimum w and b that we can use later on to make a new prediction. And this loss function, this expression for loss function, which is used in logistic regression or classification, is called logistic loss, also known as binary cross entropy. So that's why in the first slide we use, for compiling our model, we use binary cross entropy as our loss function. And you see that from TensorFlow cross losses, we imported the binary cross entropy. So when we are working, so it depends the loss function, the type of loss function that you choose for your model for logistic regression, or here for neural network, it depends on the application that you're working on. For example, if your application is classification, it's a binary classification. For example, binary classification means to determine that the tumor is cancerous or non-cancerous. The image is cat or not cat. The number is 1 or 0, just two classes, two categories. That's why we call it binary. If it's a binary classification, then from the cross losses, you should import the binary cross entropy because your application is classification, it's binary classification. But what if your application is regression, like the price of the house that we use as an example of linear regression? If this is the case, instead of the binary cross entropy as a loss function, from TensorFlow cross losses, you import the mean square error. And then mean square error is for regression applications when you're predicting numbers, not categories, like cancerous, non-cancerous, cat or not cat, 1 and 0. These are categories, these are classes, right? But price of the house was not classes, that was the number. The price of the house is number, for example, $10,000. If your application is predicting the numbers like price of the house, you are using the regression methods. And then your loss function shouldn't be the binary cross entropy. It should be, for example, the mean square error. And then here, after creating your neural network structure, you should compile your model and then put loss equal to mean square error. And then cross, I talked about cross, right? At first, cross was independent from TensorFlow, but these days cross is part of TensorFlow. So from TensorFlow, we can call cross, right? But PyTorch is another separate deep learning library that you can use. But for this course, we just use TensorFlow. So gradient descent. You remember the gradient descent, right? For example, if this was the cost function against a model parameter W, we had a hammock shape or bowl shape like this, right? If you start, for example, from this, you remember from the first session, the linear regression session. So if you start from this point, we take a baby step up until this point, which is the minimum point or the optimum point where the cost function J is minimized. When the cost function J is minimized, it means the difference between our model and the existing data is very low. It means we have a very good fit. We have a very good model. And later on, if you give another new data set that your model hasn't seen before, it can make a good prediction, right? Because you could actually get a very nice model with a low cost function or low mean error, mean squared errors, and then you can make a good prediction. And these two lines are the process of gradient descent. How gradient descent update W and B to take a baby step up to this point. And then the most important one and the costly computation and these two lines are calculating the derivative, this derivative of cost function J with respect to W and B. And computing the derivative, these two derivatives for gradient descent is used by backpropagation. And then after that, this line, when you fit your model on X and Y, you actually activate these two lines. When you fit your model, your neural network model on the training data set, X and Y, with 100 iterations, it means you're activating these two lines for updating the W and B. It update W and B again and again 100 times because the epochs is 100. It means that the gradient descent updates W and B 100 times in a loop up to the point that we get the optimum W and B, and then our model is fitted well on the X and Y. And then you can use it for more prediction. So this is the TensorFlow. You can see the logo of the TensorFlow and PyTorch. Both of them are used for deep learning applications. And as I mentioned, when we use this TensorFlow and PyTorch, you don't need to do coding from scratch. Many years ago, when TensorFlow and PyTorch were not developed, people used to code from scratch, right? But right now, you easily call, for example, dense, and then you create your sequential layers of neural network. And then you call, for example, binary cross entropy as a loss function, and then fit your model, for example, this line, fit your model, and then you activate the gradient descent to minimize the cost function and give you a best model for prediction. Just by using a few lines of code. Why? Because you have TensorFlow or PyTorch. All those functions are written in TensorFlow and PyTorch before, and then right now, today's you can use just a few lines of code by calling these libraries, and then you don't need to waste your time or takes too much time and write your code from scratch. Activation functions, alternatives to the sigmoid function. To be honest, we're tired of sigmoid function, right? Because from two sessions before, we just use sigmoid function as an activation function on each unit or core. right? But let's see that if we have other activation functions that we can use on each unit or on each node. So you remember the demand prediction example, the t-shirt being a top seller or not. So you remember this neural network, this simple neural network to see if a t-shirt is a top seller or not, a demand for that product is high or low, right? So for example, if our features or out input is price of the product or t-shirt, shipping cost, marketing, and material, then the first hidden layer, we have 3 units, and then let's say the first node calculating the affordability, and then the second unit calculate the awareness, and the third unit calculate the perceived quality of the product. And then all these are the new features, new 3 features, which is made by neural network itself. So it's something internally, which is occurred internally inside the neural network. And then the last layer, these are the input of the last layer, and then you have the output, which shows the chance or probability that the t-shirt is a high demanded or top seller or not. And for this classification application, you remember in logistic regression chapter we use sigmoid function. This stretched as function like this. G of z was 1 over 1 plus exponential of minus z, right? And this g of z was actually our activation function. And you know that g of z changes from 0 up to 1. So it is between 0 and 1. There is another activation function which is called ReLU or rectified linear unit. ReLU is a mostly used activation function in neural network. And its function is very simple. It's g of z equal to max of 0 and z. So z is wx plus b, like always, right? Wx plus b is z. And then you see that on the left-hand side of the axis, horizontal axis, when the z is less than 0 this way, g of z is completely 0. And then when we are on the right-hand side of the axis, the horizontal axis, when z is larger than 0, this area where z is larger than 0, g of z, this line, g of z is equal to z. For example, here, if z is 2, g of z is 2. If z is 4, g of z is 4. But I cannot get 4 because it changes. Yeah, it can get 4 because this one is just the sigmoid function is between 0 and 1, but this one it can get larger value, right? So this is ReLU. This is another activation functions. And in the following slide, I'm going to tell you where on which layer we can use ReLU and on which layer we can use sigmoid to make a very optimum neural network structure, right? So examples of activation functions you can see here. The first one, we call it linear activation function, or sometimes the machine learning practitioners, they call it no activation function because it's just this line and g of z is directly equal to z. So that's why sometimes we call it no activation function because there's no function. There's no function of z. It's just z itself, right? And z we know is a wx plus b. So that's why sometimes we call it no activation functions. But it's better to call it by its name, like linear activation function. And then we have the sigmoid function. You're familiar with this one, right? Then the activation value is g of z. z is wx plus b, and g of z is 1 over 1 plus exponential of minus z. And this function is changes between 0 up to 1. And the third one I just mentioned is ReLU, or rectified linear unit. And g of z is max of 0 and z. When z is less than 0, is negative, it has a negative value, g of z is 0. When z is positive, you're on the right-hand side of the coordinates, then g of z is directly equal to z. This is called ReLU. And later on, there is the fourth activation functions. I talk about it in the last slides, which is called softmax activation. But for now, let's stay with these three activation methods and build up our neural network structure. Choosing activation functions. Okay, right now you have three activation functions: linear, sigmoid, and ReLU. Okay, let's say we have this structure of neural network, two hidden layers and one output layer, right? So, and then on the other hand, we have three activation methods, right? The sigmoid one and the linear activation function and the ReLU. When we use sigmoid function as an activation function, when our application is a binary classification, 0, 1, cancerous, non-cancerous, cat, not cat, right? When your output or target, you see Y here, is 0 or 1. When it's the linear regression, it's a regression application, then you have numbers, right? Like the price of the house or the in the stock market. So because we have some negative numbers, so the price of the house cannot be negative, but when we are in the stock market and we are calculating the profits or something like that, we have just numbers. The number could be negative or positive. So when your output is a infinite number, negative or positive, you're using the linear regression applications, and then your activation function should be linear activation function, this one. When you are working on regression application, but the target is 0 or positive value, you're like the price of the house. There is no negative value as an output Y. It's 0 or more than 0. Then you should use ReLU as an activation function. But there's an advice that for hidden layers, for all the hidden layers, it's better to use the ReLU. It's better to use ReLU. Because one reason is that ReLU activation function is simpler than the sigmoid function. For example, you see that here, this is the expression or function of ReLU activation function. G of z is equal to max of 0 and z. But take a look at the g of z. It's more complicated, right? It's 1 over 1 plus exponential of minus z. The computer needs more works to calculate this function compared to this function. So that's why, that's the first reason, not main reason. That's the first reason that ReLU could operates faster than the sigmoid function. So choosing ReLU as an activation function could help you to reduce the computational cost and make your neural network faster. Another reason, another main reason actually for the speed of ReLU compared to sigmoid is that you remember that in the loss function we had derivatives of cost function with respect to W and B, right? So if you take a look at the sigmoid function, this sigmoid function as our model, then we know that the cost function J is function of our model, right? F of X or G of Z. And then you see that on the left part of the sigma function is flat, or this part is flat. What is the first derivative of a flat or horizontal line? It's zero, right? There is no there is no slope, right? It's a flat line. There's no slope. It means because first derivative means a slope, right? You remember from mathematics, high school mathematics, first derivative means the slope of a line, right? Because there's no slope here because it's horizontal, it's flat. So the first derivative of cost function j is zero. And when you draw or plot the cost function j with respect to w, with respect to this model parameter w, then you see your cost function graph is something like that, right? You have this flat area, right? Flat area. And then if you start your gradient descent calculation from here, this point, and you take a baby step and you come here, you get stuck here because it's flat. And then you get come here, take a baby steps up to this point, then you get stuck here up to this optimum point. It's not smooth, right? It's like a stir. But this one, for this one, the gradient descent is smooth. You can take a baby step and directly comes to the minimum or minimum point or optimum point. That's why ReLU is kind of faster than sigmoid function. So as an advice for choosing the activation function, as a summary or advice, for hidden layers, you can always use ReLU activation function. How about the output layer? For the output layer, it depends on your application. If you are using a binary classification, when you're working on binary classification, cat or not cats, one or zero, then the activation function on this node would be sigmoid function. If you are working on regression application with negative or positive value, the activation function here should be linear activation function. If you're working on regression, but the output is a positive or zero values, then the activation function on this node would be ReLU again, like the hidden layers. It depends on your applications. Classification, regression with either negative or positive value, or regression with just positive value, right? So far, as a summary, for hidden layers, we use ReLU activation function, and for the output layer, we use sigmoid, linear, or ReLU based on the applications that you're working on. And then here, again, from TF TensorFlow cross layers, we import dense, and then our model is the sequential of these three layers. First two hidden layers, as I mentioned, we use ReLU. And then the last or output layer, it depends on our application. If it's binary classification, activation is equal to sigmoid. If it's regression with either negative or positive, it's linear. If it's a regression application with positive, just positive value, it's ReLU. Here in this section, why do we need activation functions? So let's say here, if you have this structure of neural network, again for a top seller t-shirt, the input is price, shipping cost, marketing, and materials. And then this layer has three nodes which calculate the affordability, awareness, and perceived quality. And then we have one node on the output layer and generate the probability of the t-shirt is a top seller or not, right? So what if we use the activation function, for example, on this node, on all this node in the first layer, we use the linear activation function. And again, for the output layer, we use linear activation functions. Then this neural network is equivalent to a linear regression model that we learned in the first lecture. With this model, f of x is equal to wx plus b. So what's the point that we use neural network and actually increase our computational cost to create these neural network layers? What's the point if it is exactly equivalent to neural network? Why it is equivalent to the linear regression model? Why? Because we use linear activation functions for all the units and layer. It's not correct. If this is the case, just use the linear regression. Why you're using neural network? And for example, for the sake of simplicity, you consider this simple structure of neural network. Input X, the hidden layer, the output layer, with just one unit for each layer. So the first one, in this node, it calculates the model parameter W and B. It's W1, W11, B11, and then we have model parameter in the output layer in this unit, W21, B21, right? So, and then here, if we use the linear activation function on this node, then the activation value, this A superscript 1, the activation value is going to be W11X, the input, plus B11, this B11 here. How about the activation value of the second layer or output layer? It is going to be W21. And then here, instead of X, we use the output of the first layer because right now for this layer, the input is not X. The input is A superscript 1. So we use A superscript 1 here plus B21, B21. And if instead of this one, instead of this A superscript 1, which is this one here, we use this expression instead of A superscript 1 and put it here instead of replace this A with this expression, we have this one. We have this expression. After rearranging this, the right-hand side of this equation, we get such expression. Then in the parentheses is kind of equal to a W, and then this one could be a bias parameter B. And it seems that it's like Wx plus B. What was Wx plus B? The linear regression model. So our neural network, this neural network is exactly equal to linear regression when you use linear activation functions on each nodes. So don't do that. If you want to use neural network, you cannot use linear activation functions for all nodes on each layer because it ends up with this linear regression model. So just directly use linear regression model. What's the point that you use neural network, right? Or here, if you stay with in the hidden layer, so you can see this structure, right? So we have three hidden layer, and then we have the last layer, the output layer, right? So if you stay with linear activation functions for all the nodes three hidden layer, on three hidden layers, and then for the last one, again, you use linear activation functions, then this neural network is equivalent to the linear regression, to the linear regression. Another case, if you use linear activation functions for all the nodes on hidden layers, these three hidden layers, and you use sigmoid activation functions on the last or output layer, then this neural network is equivalent to logistic regression model. So if your neural network is equivalent to linear regression, or this case, this scenario, your neural network is equivalent to logistic regression, what's the point that you're using neural network? So that's why the most important advice in this session is don't use linear activations in hidden layers. Instead, use ReLU for the hidden layers. Use ReLU activations for hidden layers. Okay, so this is section 3. I'm gonna uh give you 10 minutes break. So now it is 3:27. Please come back at 3:40, just 10, 12 minutes. And then I'm going to introduce the softmax activation function. And then I think it's the last section of this session.
Okay, sir.
Okay, thanks. 10, 12 minutes. 3:40. Okay, can you see my screen?
Yes, professor.
Okay. Okay, let's get back to the grind. So the third section, multi-class classification. So the multi-class classification is on the other side of the binary classification. So for binary classification, as I mentioned many, many times, we have just two classes, right? For example, the tumor is cancerous or non-cancerous, the image is cat or not cat, or the number is 0 or 1. Just two classes, two categories, right? So we call it binary classification. But multi-class classification, as you can see, it has multi-classes. It has more than two classes, right? For example, this data set of handwritten digits from MN or MNIST, the this MNIST is standing for I don't remember the M, but it's something National Institute of Standard and Technology. There are a lot of data set for machine learning and computer vision applications. So as you can see here, the output against the binary classifications that we had just two classes, 0 or 1. Right now, the output or the y hat could be 10 numbers or 10 classes, right? From 0, 1 up to 9. For example, if you want to scan a postal code or the barcode, right? So if we have the postal code or zip code on an envelope, right? You use 10 numbers from 0 up to 9, right? So if this is the case, we call it multi-class classifications because the output is more than two classes, right? For example, if this is an image, so the Y could be 7, right? Or it could be 8, or it could be 9, or it could be 0 or 1. It doesn't have just two outputs for Y, right? It could be any of these numbers. So multi-class classification problem, target Y can take on more than two possible values. For example, if you take a look at these two figures, the left-hand side figure shows the binary classification. If you have this data, you can draw the binary classification can draw this decision boundary and make two classes. The first one, the class 1, with the probability of y equal to 1 with this given input x, and this is the probability of y not being 1, two classes. But if you take a look at this data set, you can see that the decision boundary of the multi-class classification could be something like this. Divide this area into four sub-area or subsets. The first one with the probability of y being 1, the second one, the probability of y being 2, third one, y being 3, and the fourth one, the probability of y being 4. As you can see here, we have four possible values for y, 1, 2, 3, and 4, right? So that's what we call it multi-class classification because we have more than two possible values. So you remember for the logistic regression chapter, we had two possible output values. Then z was wx plus b, and then we used the sigmoid function g of z, 1 over 1 plus exponential of minus z, which shows the probability of y being 1. And then if we want to follow the neural network notation, let's get this g of z equal to a subscript 1. And then you know that if the possibility or the chance of y being 1 is, for example, 0.71 or 71%, then based on a statistical rule, then the possibility of y not being 1 is 1 minus 0.71 or 0.29 or 29%. These two probability, if you add up together, it should ends up equal to 1, right? So if it is the first activation value, A1, then A2 would be 1 minus A1, which shows the probability of y not being 1. This is for logistic regression. We have two activation value because we have just two possible output values. But for multi-class classification, right now I'm gonna introduce the softmax regression as an activation function. Let's say we have four possible outputs, 5, 6, or 9, or 10 possible outputs. But here, let's say we have four possible outputs. Then the Z1, which is for red cross classes, the data set of with this notation, red crosses is W1X plus B1. And then Z2 for the second class is W2 times X plus B2. Z3 W3 dot X plus B3. Z4 W4 dot X plus B4. And then the activation value for the first class, A subscript 1, is equal to this fraction. In the numerator, we have exponential of Z1. Z1 is defined here for the first class. And then in the denominator of this fraction, we have the summation of exponential of these four z's. Exponential of z1 plus exponential of z2 plus exponential of z3 plus exponential of z4. And then this activation value, a subscript 1, shows the probability of y equal to 1 with this given input x. And for A2, activation value for the second class, in the numerator of this fraction, instead of exponential of z1, we have z2 because we are dealing with the second class, and then the same denominator of the fraction. This fraction shows the probability of y being 2. The same thing for the probability of y being 3 and 4. So in this way, we generated four activation values for four possible outputs in multi-class classification application, right? And then here, let's say A1, A superscript 1, the activation value of the first class shows the probability of 0.3. The A subscript 2 shows the probability of y being 2 with 20%, 0.2. A3 is 0.15. What is the A4 value? It must be 0.35. How I can calculate this 0.35 if I have the probability of these previous three classes? Because based on the statistics, the probability of these four, if you add up together, there should be 1, right? So for calculating the probability of the last one, we can calculate it using 1 minus 0.3 minus 0.2 minus 0.15, and you get 0.35. So the general expression for softmax regression with n possible output, let's say y, the output, is from 1 up to n, right? Then the z, for example, we had z1, z2, z3, z4 here. To put all these 4 or n equations in a general expression, you can write it here. Z subscript j equal to w subscript j times x plus b subscript j. And j changes from 1 up to n because we have n outputs. And then this expression, these 4 fractions, can be expressed in a general equation like this. Aj, j changes from 1 up to n because we have n outputs for multi-class classification, equal to, in the numerator, exponential of zj divided by summation of all the exponential, equal to the probability of y being j with the given x as an input. And then note, a1, a2 plus a3 plus a4 up to a subscript n must be equal to 1. Like here, the summation of all these probabilities for y being 1, 2, 3, 4, if you add up together, you get 1. So this is the equations for softmax regression as an activation function if you're working on multi-class classification. So if you compare the logistic regression with binary classification and softmax regression or multi-class classification, you can see the Z for logistic regression in chapter 2 was Wx plus B. A1 or G of Z is 1 over 1 plus exponential of minus Z, which shows the probability of Y being 1. And A2 shows the probability of Y not being 1, which is 1 minus A1, right? And then this was the loss function. You remember from chapter 2, for the loss function for logistic regression or binary classification was minus y log of a1 minus 1 minus y times log of 1 minus a1, right? And then log of a1 if y is equal to 1. And this is like log of 1 minus a1 here. This shows the probability of y not being 1 or y equal to 0. And then for the cost function j, you remember you get the average of loss function. For the softmax regression in multi-class classification, A1 up to AN are written in this way. As I mentioned, for 4 classes or 4 possible outputs, you had A1 up to A4 using these 4 fractions. You have the same thing here. And then for multi-class classification, the loss function is cross entropy loss, which is this equation here. The loss function is function of A1 up to AN and Y. If Y is equal to 1, the loss function is going to be minus log of A1. If Y is equal to 2, then the loss function is just minus log of 2. If y is equal to n, the loss function is just minus log of a subscript n. For example, if y is equal to j, then the loss function is minus log of a subscript j. And then minus log. If you see the minus log from mathematics, you see that the loss, the minus log against a subscript j is this curve, right? And you see when aj is too big, the loss function is 1. And then when aj is very small, for example, this area, you see the loss function is very large number. Why? Why when, for example, aj is very large, the loss function is almost 0, this area? When aj, what was aj? You see a for any arbitrary class, 1 up to n or aj, shows the probability of y being one of those possible outputs, right? If a is very high, it means the probability is very high. It means the probability of, for example, y being 1 is 100%. So it means that your prediction is 100% true. You could you could recognize that that data is related to one classes with 100% accuracy, with 100% chance. So if this is the case, it means the loss function is 0, because loss function shows the difference between your prediction and the data. When you predict the 100%, it means there's no loss, there's no error. So the loss function is 0. When a or the probability is too low, it means there is a huge difference between your prediction and the data. So the loss function is very large. So minus log is a good choice to show the loss function, right? For this softmax regression. So neural network with softmax output. So for example, this is again a structure of your neural network with hidden layers, 2 hidden layers, and 1 output layer. As you remember, as an advice, as an important advice, for hidden layer, we just use the ReLU activation function. But now here, for the output layer, we're going to use softmax output if you're working on multi-class classification. For example, here, you have this structure of neural network. You have the first hidden layer, the second hidden layer, and because you're working on multi-class applications, your output is more than 2 possible values. So the output layer has more nodes, right? For example, 10 units, because you're working on multi-class classification with 10 classes or 10 possible outputs. For example, 10 numbers, right? You're working on a postal code or zip code on an envelope. So there are 10 numbers. So the output would be 10 classes. Or your as a medical application, you want to see the disease of a patient. There are 10 possible diseases, right? Or I don't know, 10 car brands, right? So the image is for BMW, is for Mercedes-Benz, is for Honda, Hyundai. There are 10 brands, there are 10 classes that can be the output of the neural network, right? That's why we call it the multi-class classification, because the output could be 10 classes, could be 5 classes, more than 2 classes. And then if you consider softmax regression or softmax activation function for the output layer, then the Z1 for the first node is this one, and A1 is the activation value of this node, the output of this node, up to the last one, Z2 is WA2 plus B10. And then the output of this node, which is A310, is this softmax regression model. The first one shows the probability of y being 1. The last one shows the probability of y being 10. One thing that you should keep in your mind when you're working on logistic regression, the A or the G of Z, for example, the first activation value of the third layer is just function of Z1. A2 is just function of Z2. But if you take a look at softmax activation functions, the A is function of A1 up to A10, or the A, this output here, is function of Z1 up to Z10. Why? Because on each activation function, for example, this activation function is just for the first node, A1, for the first node of the output layer. But this A1 is function of exponential of Z1, exponential of Z2, up to exponential of Z10. It's function of all of them, all the Z's from 1 up to 10. But this is not seen in logistic regression. And the activation value of the first unit is just function of Z1. The activation of the second unit is just a function of Z2. So if you want to write the code for multi-class classification, again, you import TensorFlow as TF. From TensorFlow cross import sequential. From TensorFlow cross layers import dense, and then create your model, your neural network model, which is the sequential of 3 layers. I'm talking about this structure. The first layer with 25 units, and you know that for the hidden layer, we just use ReLU activation function. The second hidden layer with 15 units, activation function is ReLU. And then for the last one, it has 10 units, and the activation is softmax, as I mentioned, for multi-class classification. And from TensorFlow cross, for the losses of this application, this multi-class classification, we import this loss function. It is called sparse categorical cross entropy. And then you compile your model using this loss function for multi-class classification. And then you fit your model on the data with 100 iterations for gradient descent. But this is not the best version of writing such code. In the following slide, I'm going to tell you how we can optimize this code. But the steps are like this. The first step, creating your model. The second step, specify the loss and cost. And then the last step is to fit your model or train your model on the data to minimize the cost function J. Why I said it's not an optimum way to write such code. So for example, you consider this fraction, 2x is equal to 2 over 10,000. You can actually decompose this fraction in this way, right? Instead of write directly 2 over 10,000, you can write it down like 1 plus 1 over 10,000 minus 1 minus 1 over 10,000. It is exactly the same as 2 over 10,000. But if you calculate these two options, if you try these two options on Python, you get these outputs. The first option, 2 over 10,000, you get this number as an output, 0.002, and then the 0 digits after 2. But if you try this one, option 2, here, and then print it out, the output would be 0.00, instead of 2, it's 19999, right? So for a small calculation, this difference is not that much and it doesn't affect your result. But imagine you have 10,000 iteration, right? And then this error, this difference between these two outputs accumulate, right? We call it the round of error, numerical round of error, right? So what we can do, because it depends on the operation of your computer, right? For example, 2 over 10,000 is rounded off to 0.002. But if you break it down in these two parentheses, then the computer first operates on this fraction and then do the operation on this parentheses and then add them together, right? Because you change the order of operation of your system, it might generate more accurate output. But if you directly ask the computer to calculate 2 over 10,000, it's rounded off to this number. So we want to do the same thing for these lines of code to make it more accurate, more efficient. What we can do is here like this. So for example, for logistic regression, for binary classification, first you can build up your neural network model, sequential of 3 layers. The first layers, dense layer with 25 unit ReLU activation function. The second hidden layer, the second dense hidden layer with 15 unit and activation is ReLU. And the last one, the activation is sigmoid because you are working on logistic or binary classification. And then you compile your model and the loss function is binary cross entropy. This one here. But how you can optimize this one? You see, in the sigmoid, in the logistic regression, you remember the activation function or g of z was 1 over 1 plus exponential of minus z. You calculate the a using this fraction, this equation first, and then it's an intermediate value. You calculate a first, and then you use this a to calculate the loss function, minus y log of a, this a, you just calculated on the top, minus 1 minus y log of 1 minus a, this one. This arrange, this order of calculation is like 2 over 10,000. It's not more efficient. It has some round of error. But instead of calculating the a first and then put it inside the loss function, you can directly, is the more accurate loss in code is to directly replace this a with this equation here, with this fraction. And then the loss. So to be honest, if you take a look at these two approaches, you think that it doesn't matter to calculate a first and then put it here. But here I'm saying that don't do that. Instead of calculating the a first and place it here, directly put this fraction on here like this. And let the computer to choose how it operates. Let the computer to choose how to calculate this loss function. Because if you follow this pattern, the computer knows how to calculate and the output would be more efficient. To do so in your code. So take a look at this part. We are just talking about logistic regression, binary classification, not multi-class. For logistic regression, binary classification, the model is sequential of 3 layers, and the last layer, the output layer, the activation is sigmoid, and the rest of it is ReLU. And then compile the model using this binary cross entropy loss function. But if you want to do something like this on your loss function, you should write these lines of code in this way. Again, you build up your model using the sequential of the first hidden layer, the second hidden layer, but on the last layer or output layer, instead of sigmoid activation, you put linear, and then instead of model, this one, model compile loss equal to binary cross entropy, you can modify this one by this line. Model compile loss equal to binary cross entropy from logits equal to true. What is logits? Logits is actually Z. Logits is equivalent to Z. What is Z? This one here. It's like instead of calculating the A first as an intermediate value and replace it here in the loss function, you directly use this equation in the loss function. And in this way, writing a code in this way, and then from logits equal to true, you let the computer to calculate the loss function in this way, in the more accurate way, with less round of errors. This is visible when you are doing very large computations, when you're using a large neural network. Yes, for small applications, for a small data set, it's not that much visible, this round of error, but when your calculation is very large, when you're using a large neural network or large model, then this round of error might affect your output, the accuracy of your predictions. The same thing for multi-class classification. So the model, you use the sequential of 3 hidden layer, and then the last one, instead of using softmax, you replace it with linear activation model, and then you compile your model instead of directly use model compile loss function. You use model compile loss function, and then you activate the logits. What was logits? The Z. You activate this one. So you remember this was the loss function of the multi-class classification. If y is 1, loss function is minus log of a1. If y is 10, it is minus log of a10. But a1 and a10 are calculated in the previous step. But we don't want to do that. We want to put a1 directly here in this equation, like this. And instead of a10, we put a10 equation directly inside the loss function and let the computer to do these operations by itself. And it reduced the round of error by activating the logits, the logits, right? The Z, to be directly inside the loss function. In this way, by writing the code in this way, you can optimize your multi-class classification or binary classification like this. And this is the whole code. This is the whole code for multi-class classification. So you import TensorFlow as TF. From TensorFlow cross, you import sequential. From TensorFlow cross layers, you import dense. Build up your model using the sequential of 3 layers. First hidden layer with 25 units, activation ReLU. Second hidden layer, 15 units, activation function ReLU. And then the last output layer, it's a multi-class classification. You should use softmax function as an activation. But as you remember, to reduce the round of error, instead of softmax, for now, we put activation equal to linear, and then we call our loss function for the multi-class classification, which is sparse categorical cross entropy. And then we compile our model using this loss function, the sparse categorical cross entropy, but we activate the logits by from logits is equal to true. And then fit our model on the training set with 100 iterations, the time that the grade it takes for gradient descent to optimize the model parameters. And then for prediction step, the logits is equal to model X. And this is not A1 or A10. This is not the output of the neural network. This is not supposed to be the output of neural network because here we change the softmax to linear. We want to get back to softmax again, right? So after we got the model of X, the training set, we get the logits. We should use TensorFlow neural network softmax. We should get the softmax of the logits. And this line gives us the prediction, the A1, A2 up to A10. But the logits, as you remember, it's Z1, Z2 up to Z10. So if you want, I want to show you a neural network structure. You see, the output of the neural network must be A value, right? The A, the activation value, not the Z value. But here, when you use this modification, this logits, this model gives you the Z value, not the A value. But we know that the output of the neural network is A value. So by writing this line, softmax of this logit, softmax of the Z's gives us the A values, which is our predictions, which are our neural network outputs. So in this way, you can optimize your code in multi-class classification. Or this one is the modified one for logistic regression or binary classification. The same thing. Sigmoid, sigmoid, but this one, the last one, instead of sigmoid, we use linear, and then we compile our model using binary cross entropy loss function. We activate the logits, fit our model, but our model generates logits, the Z. And then in the last step for our prediction, we get the sigmoid of the logits, which is our output. For example, the sigmoid of logits is f of x, or the probability. For example, it is 0.7. It means 70% chance for y being 1. And I want to just introduce this one, the multi-label classification. It's just a theory that you know at least about the multi-label classification. And then I finish this lecture. So imagine this. We have these 3 images. And then we have 3 questions. Is there a car? Is there a bus? Is there a pedestrian in the image or not? If you take a first image, Is there a car? Yes, there is a car. Yes. Is there a bus? No. Is there a pedestrian? Yes. So yes, no, yes. The second one, is there a car? No. Is there a bus? No. Is there a pedestrian? Yes. The third one, is there a car? Yes, there is a car in this image. Yes. Is there a bus? Yes, there is a bus. Is there a pedestrian? No, there is no pedestrian. Yes, yes, no. And then this yes or no can be shown in this way. So Y for the first image is 101. 1 refers to yes, 0 refers to no. The second one, Y is equal to 001. This one, Y is equal to 110. So you remember for the binary, for example, classification, we had just one label. For example, you give this image, the first image, to your model, and then the model tells you that this image is cat or not cat. But for multi-label classification, if you give this image, the first image, to your model, it gives you this output with three labels. It's not just about cat or not cat, or a car or not car. It gives you three answers just with one output. It means we have three labels with just one output. For example, it tells you with one output, you give some information about the car, if the car exists in this image or not, about the existence of bus, about the existence of pedestrians. So our output, each output has three labels, right? That's why we call it the multi-label classification. And then the neural network for multi-label classification could be something like that. We can create three small neural networks, one binary classification for car. This A shows the probability of the image being car or not car. This one for the image, uh, the bus exists in the image or not. The third neural network shows the probability that the pedestrian exists in the image or not. Or you can add them together, add this or string these three small neural network together and get a bigger neural network, and then use the sigmoid activation, and then you get this output. This output has three numbers, not just one number. Like binary classification, you remember, for example, for a tumor to be cancerous or not cancerous, the output was just one number, for example, 0.7, 70% chance that the tumor is cancerous. But here for multi-label, the output doesn't have just one number or one label. For example, for this application, it has three values or numbers. It shows the first one shows the probability the uh, uh, of the car in the image. The second one shows the probability of bus in the image. The third value shows the probability of pedestrian in this image. That's why we called it multi-label classification. And it's just one thing that I want to mention because it's very important. There's another advanced optimization method because so far we just used gradient descent. And you remember the gradient descent? That was this was the process of the gradient descent to update the W using the learning rate and this first derivative of cost function with respect to J. And you remember that the cost function, the contour of the cost function with respect to W1 and W2, two parameters, is something like this. right? For example, if if you start from this point and take a baby steps and then come here, take another baby step, we come here and come here, here up to this minimum point or optimum point, right? And you see all our steps are in one direction. So if all the steps are in one direction, don't you think that we can take a bigger step because all of them are in one direction, right? So instead of a small step, we can take a bigger step to reach out this minimum point faster. And how you can increase your step size by increasing the learning rate alpha here, learning rate alpha here, right? Or the opposite case, the opposite scenario is this one. If you start your gradient descent from here, and then at first you take a very big step, you come here, take another big step, you come here, and then here, up to the minimum, up to the optimum point. You see, there are a lot of larger steps with back and forth, left to right, left to right. Don't you think that if you maybe decrease your step size by decreasing the learning rate alpha, you can reach out the minimum point faster? Yes, you can do that. And what is the optimization algorithm that can adjust the value of the learning rate alpha? For example, in some steps, in some stages, it can increase the alpha value, and in some steps, it can decrease the alpha, adjust it, right? Right? It can more optimize your cost function, right? It's it can do better than the gradient descent because in the gradient descent, the learning rate alpha is constant. There's no change. But imagine that there is a method like gradient descent, but it can adjust learning rate alpha. If it is like this case, it can increase the alpha. If we are in a position like this case, it can decrease the alpha. There is an algorithm, there is an optimization algorithm. We call it the Adam algorithm. It does the same thing that I just mentioned. So here, instead of following these operations, which is for gradient descent, instead of that, you can use Adam algorithm. Adam stands for adaptive moment estimation, and these three first letter ADA and this M, add them together, it makes Adam, adaptive moment estimation. So Adam adjusts the learning rate A in gradient descent and optimize your model parameters faster. So here, for example, in the code, after building up your model using cross layers dense layer, then here, when you're compiling your model, change your optimizer to Adam. Optimizer equal to TF cross optimizers Adam. But for Adam, you need to define this argument. You need to define an initial value of the learning rate. For example, let's say 10 to minus 3 or 0.001. You give this initial value of the learning rate to your model, and then it adjusts this value by itself. It might increase it a little bit. It might decrease it a little bit. This is Adam optimization algorithm job. And then you have the loss function and feature model. But if you don't do that, if you don't define your optimizer, then by default, it takes gradient descent. But you can here, when you're compiling your model in the parentheses as an argument, you can define your optimizer to be Adam instead of gradient descent because it's more efficient. It can adjust the learning rate. It can control your steps when you're using gradient descent to optimize your model parameters. But this session, I think from page 1 up to page 17, it's enough, but the rest of the pages are just some additional sections. If you like, you can take a look at it. It's about the convolutional neural network. I'm not gonna touch this convolutional neural network, which is another type of layer of neural network. Let's maybe talk about convolutional neural network in the next session, but here I'm gonna finish this chapter, chapter 5, here on page 17. Do you have any questions? If not, we can call it a session. And by the way, next week we have in-person class, so we can see each other. If you have any questions, concerns, we can talk in person. And we have a quiz in the next session. So you're gonna write your quiz uh, from chapter 4 and 5, the neural network, introduction of neural network, the structure of neural network, activation functions, TensorFlow, and all the stuff that I taught in the past 2 sessions. Any questions?
Hello, Professor. I
No,
have a
sir.
question. Um, could you give us some example practice problems?
Your practice what?
Um, example practice questions.
Okay. You want to practice some questions?
Yes.
What do you mean? What should I do?
Because I don't know wh which questions I we need to have a have.
It's like the first quiz. The multi-choice questions, true, false, and if I can find some hand calculation questions, I don't think that I can find hand calculation questions for this quiz. So most of the questions would be multi-choice questions. For example, the types of the layers. I don't know, for example, what kind of activation functions is appropriate for hidden layer, for the output layer, what are the optimization method, what is the Adam optimization method. Adam is faster or gradient descent is faster. When we can use softmax activation functions, something like that. Multi-choice questions or true false, something like that. Something like the exactly like the first quiz, except hand calculation questions. I might find some hand calculation questions for the quiz, but most of the questions are multi-choice questions, just the theory, right? I don't want you to write a code or something like that. I might bring some part of the code, right? And just ask you some questions about, for example, this sections here. I might brought, I don't know, a few lines of the code and ask you about these lines. Why we use, for example, linear, why we didn't use softmax or sigmoid function directly, something like that. But it's not descriptive questions. It's just multi-choice questions. I try to actually design multi-choice questions, but you should be ready for everything. It's clear?
Yes, thank you.
No problem. Any questions? Okay.
So,
Yeah.
like, will there be any more assignments, sir? Like in the future?
Yeah.
Okay.
Yeah.
Okay, sir.
Okay. If you don't have any questions, you're excused, but I think someone want to talk to me. That guy can stay, but rest of you, you're excused. You can leave the session.
Thank you, Professor.
Yeah, no problem.
Thank you, sir.
No problem.